Have you ever stood by the water and looked at a massive cargo ship? I mean, just a mountain of steel, and thought to yourself, how is that even possible? Well, today we are going to unravel that exact mystery. We're talking about how incredibly heavy things float. I mean, really think about it. You can have a 200,000-ton steel ship floating like it's no big deal, but you toss a tiny little pebble in and it sinks straight to the bottom. It just doesn't make sense, right? It feels like it breaks the rules of logic, but what it actually follows is the rules of physics. So let's dive right into this, what I like to call the floating paradox. Our intuition, our common sense, just screams that heavy things are supposed to sink. I mean, look at this. A stone pebble sinks instantly. A steel cargo ship floats effortlessly. But here's the real kicker. Steel is about 3 times denser than rock. So if anything, the ship should be more likely to sink. This tells us something absolutely crucial. The weight of the material itself isn't the whole story. Not even close. To get to the real answer, we actually have to go way back. We're talking more than 2,000 years, to ancient Greece, and to one of the most famous aha moments in the history of science. So, the story goes, the great thinker Archimedes is getting into a full bathtub. As he gets in, he watches the water level rise and spill over the edge. And in that moment, something just clicks in his brain. The volume of water that spilled out was directly connected to the volume of his own body that went under the water. He had just stumbled upon the concept of displacement, and it was so profound, he supposedly ran through the streets shouting, "Eureka!" And that bathtub realization led to his famous principle. Now, pay close attention to that phrase, loss in mass. Obviously, an object doesn't actually get lighter when you put it in water, but it feels like it does, right? That feeling is the entire key. It's the water pushing back. This little diagram shows that upward push perfectly. We call it the buoyant force. So check this out. The scale on the left shows the object weighs 6 kilograms in the air. But when it's in the water, the scale only reads 2 kilograms. So where did that other 4 kilograms go? It didn't vanish. It's being lifted up by the water. And that buoyant force is exactly equal to the weight of the water that got pushed out of the way. This upward force, well, it changes everything. So how does a little upward push from water explain a massive floating ship? Well, it all comes down to a kind of great balancing act. Okay, this is the single most important rule to remember. An object's weight, gravity, is constantly pulling it down. At the same time, that buoyant force from the displaced water is pushing it up. When those two forces are perfectly equal, the object floats. It's like a perfect tug of war where neither side wins. Let me put it another way, which you can see right here. For something to float, the mass of that object has to equal the mass of the water it displaces. It really is that simple. This is the golden rule of flotation. So what happens when those forces aren't in balance? Well, you get 3 different outcomes. First, let's look at something that's positively buoyant, like a cork or a beach ball. Here, the upward push from the water is way stronger than the object's own weight, so it shoots to the surface and floats really high. In the second scenario, the forces are in that perfect equilibrium we talked about. The object's weight is a perfect match for the buoyant force. This makes it neutrally buoyant, and it'll just hang there, suspended in the water, not rising, not sinking. If you've ever seen a submarine just hovering in place underwater, this is what's happening. And finally, we come full circle, back to our little pebble. It's negatively buoyant. The downward pull of its own weight is just way, way stronger than the upward push it gets from the tiny amount of water it displaces. That water just doesn't have enough oomph to fight back, so down it goes, straight to the bottom. All right, now that we've got the physics down, let's talk like the engineers and sailors do. They use these laws every single day, and to do it, they have a few key terms. It's kind of like a ship's secret language. First up is a word you'll hear all the time, draft. And it's super simple. It's just how deep the ship's sitting in the water. The heavier you load a ship, the more water it has to displace, so the lower it sinks. Its draft increases. It's a really quick visual way to get a sense of the ship's total weight. Next is an absolutely critical safety feature, reserve buoyancy. Basically, this is all the watertight space on the ship that's above the waterline. Think of it as the ship's safety margin, its backup floating power. It's what allows the ship to take on a huge wave or shift its cargo without getting swamped and sinking. And this This is where the science gets incredibly precise. It's called TPC, which stands for tons per centimeter immersion. It tells the crew the exact answer to this question. How many more tons of cargo do we need to load for the ship to sink by 1 more centimeter? It is a vital, super practical calculation they use every day. Okay, enough theory. Let's get our hands dirty and see how all of this plays out in a real-world example. So here's our scenario. We've got a simple, boxy barge. All by itself, empty, it weighs 180 tons. Our job is to load it up with an extra 360 tons of cargo. The question is, how much deeper is it going to sit in the water once we're done? And you know what? The process is actually pretty straightforward. First, we just need to find the new total weight. Then, using that law of flotation we talked about, we'll figure out exactly how much water it needs to push aside to stay afloat. First, the easy part. The barge itself is 180 tons. We add the 360 tons of cargo. A little simple math, and that brings our new grand total weight to 540 tons. And this brings us right back to our golden rule. To stay afloat, the barge now has a new downward force of 540 tons, and to balance that, it needs an equal upward force. So it has to sink into the water, just enough to push aside a volume of water that also weighs, you guessed it, exactly 540 tons. So if we know the barge's dimensions and the density of water, we can calculate exactly how far it needs to sink to do that. And the math tells us that the barge will settle in the water until its draft is precisely 1.2 meters deep. The physics is perfect and predictable every single time. So we did it. We unraveled the paradox. It isn't about how heavy the material is, it's about how the shape of the ship's huge, hollow hull displaces a massive weight of water. That displacement creates a buoyant force strong enough to hold it up. But, solving one mystery just opens up another one, doesn't it? We now know how a ship floats, but what on earth stops it from just tipping over? Well, that is a story for another day.